In this video, we're going to start looking at a second way to use accumulators, which is to make a recursive function or a set of mutually recursive functions tail recursive. But first we have to understand what tail recursion means and why it matters. So I'm sitting here in sum tr-starter, and I phrase this as a problem. The problem is to consider the following function that consumes a list of numbers and produces the sum of the numbers in the list. And we're going to use the stepper to analyze the behavior of this function as the list gets larger and larger. So let's first quickly review the function. This is a function we've seen before. It consumes list of number, produces number. It's the sum of all the elements of the list. There's a couple examples. And again, what you can see here, what you should be able to see by this point in the course, is quickly have the structural recursion on a list template pop out at you. I'm highlighting it here. So it pops out at you, and then in particular, your eyes should focus on the places where we filled it in. And basically, when the list is empty, we produce 0. Otherwise, we add the first element to the natural recursion. We've seen this function before. What does it mean to use the stepper to analyze the behavior of this function as the list gets larger and larger? Well, let me just do that. Let me just say sum of, I don't know, list. And to keep it simple, I'll just say 1, 2, 3, 4, 5. That's an expression, and now I'm going to step that expression. So I'll use the stepper. I've got intermediate student language turned on here because that makes the stepping look better. I usually step with intermediate student instead of intermediate student with lambda, unless I'm actually using lambda expressions. So here we go, let's step. And let me shape this a bit like this. And what I'm actually going to do is step through it kind of quickly a bit. So there's the first call, and I'm just going to step through. And we get to a point where we're at +1 and the natural recursion. Let me put this like here. Let me make this fit nicely. So we get to this point where we're at +1 and then the natural recursion of the rest. The rest, of course, is list 2, 3, 4, and I'll keep going. And now we're at +1, +2, and the sum of the recursion. +1, +2, +3, the sum of the natural recursion. And eventually, this is going to get to +1, +2, +3, +4, +5, and the sum of empty, which will come back as 0. And what you can see here is we've got all these pluses built up waiting to happen. And then kind of at the very end, bang, 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 all those pluses will happen, and we'll end up with 15. So now the question is, what happens as the list gets long? Well, it's easy to see what happens. What happens as the list gets long is that this pending computation, this set of pluses that are waiting to happen, is going to get longer and longer. If the list is 1,000,000 elements long, this is going to get to be 1,000,000 plus 1 for the 0, the empty, or I guess it'll be 1,000,000 pluses. Does that matter? Well, it turns out it does matter for the following reason, which is that what Dr. Rackett has to do to make ISL programs run quickly, what any programming language has to do to make programs like this run quickly, is it stores this saved context. It stores this saved context in a special part of the computer's memory called the stack, which happens to be very limited and very expensive. And so what that means is that we want to try not to use it unless we need to. And it means that if we could find a way to add up long lists without using proportionally more stack, that would be better. That would be better. We'd like to not build this up. So the question is, why did this get built up? So the answer has to do with a couple of new concepts known as tail position and a function call in tail position and a recursive function call in tail position. There's 3 separate concepts. Let's look at them. The reason it got built up is, let's look right here at this plus expression. Now that plus expression sits in what's called tail position. Because the result of that plus expression, whatever it is, will be the result of the enclosing function. Just look at it. You can see that according to the rules of evaluation, if the first question is false, then we get to the second con clause. It's an else, so the entire con gets replaced by that plus. Whatever that plus produces is the entire result of sum. So whenever an expression is in that position, whenever an expression is in a position where its result, without anything else happening to it, would be the result of the enclosing function, that's called tail position. Okay? Just to be sure we're clear on tail position, here's a couple other examples that I want you to look at.